Welcome to today's webinar. The topic today is geotechnical analysis in Rfem 6, constraint, modulus, method, and anchor. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the webinars, the technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Juliane Stopper-Aktak. The presentation will be done by Mark Gebhardt. He's responsible for customer support and also for the development of the add-on geotechnical analysis. And also Juliane Stopper-Aktak is responsible for the development of the add-on geotechnical analysis. Yeah, and she works also in the customer support team. Okay, for the attendees who participate the first time, I'll say some words how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Mark. Mark, it's your turn.
Thank you, Andreas, for your kind introduction. Now let's start over with two exciting new features of the geotechnical add-on for Rfem 6. First, we would start with the soil representation type 2D constraint modulus method and going over to the new member type anchor. And at the end, I would show a little outlook for new features coming for the geotechnical analysis add-on. So now we start with the new 2D constraint modulus method. This was a formal version of Rfem 5 implemented as Rf Säulen. Now it is available as a 2D constraint modulus method. Therefore, you have to activate the geotechnical analysis add-on and select a soil massive. Afterwards, the soil structure interaction can be handled via generated spring stiffnesses. They are depend on the soil properties, such as the layers and material, as well as the load and the foundation geometry. Now I would describe the method. The constraint modulus method implemented here use the iterative calculation of the subgrade reaction parameters by iterative comparison of the soil contact stresses. So if from the former iteration and the actual iteration the contact stresses are equal, the settlement calculation will be done using the constraint modulus method and gives back spring stiffnesses as elastic support coefficients. They are available for, first of all, the surfaces and additional for the lines to get additional stiffening from the adjacent soil. Now we'd go to the Rfem 6 and load the model from a former webinar and would show you the place you can also download it. Here it's the webinar Geotechnical Analysis with Construction Stages, and there was a 3D analysis with a nonlinear material behavior based on the hardening soil model. You can download the file down there with a building and already a 3D soil generated. So go back to Rfem 6 and we see it's already loaded. Now we will change the base data. First of all, in the 2D constraint modulus method, we don't need any more construction stages. So we can deactivate them, but we need the geotechnical analyzers. So moving forward, the DSA things are deleted, and we see there are already materials defined. They're using the modified hardening soil, and as you see here, they have also basic material properties which rely on the loading, unloading Young's modulus. If this is really true for a 2D linearized behavior, it's not completely sure, so maybe for a real project you have to check. But now, to simplify, we just go and select linear elastic, and we see Young's moduli of the soil materials are changed, and the behavior is now linear elastic. Furthermore, we don't need any more surface contacts. At the moment, the building is 10 centimeters above this upper soil surface. And we don't need this anymore because the springs are generated automatically generating springs, finding the surfaces when they are in the upper surface of the soil massive. So we go to special objects and delete all surface contacts. Afterwards, we move our building 10 centimeter in Z direction. Now, the base surfaces are touching the soil massive. Now we take a look to the soil massive itself. In geotechnical analysis, you find the boreholes, which are already defined by the other webinar, with the former shown soil materials. By them, a soil massive is generated, at the moment in 3D, but we want to change it to the 2D constraint modulus method. Now we see the additional settings tab is open. And here you have to select where the supports will be generated. So you can select the surface by hand or use the automatic detection. Furthermore, in the future, it will be available to select on which parts of the surfaces, such as only surfaces, lines, and nodes, the elastic support coefficients will be generated. And you can select to get nonlinear behavior on the surfaces and the lines supports. But the constraint modulus method already have a failure under tension. Additional to the generated supports in vertical and shear direction, in horizontal direction, fixed supports can be defined here. And on the last point, you can select rock beneath the last layer, which say that the soil massive is under this last layer, completely fixed, supported, and no settlement will be happened, and stiffness will be very, very high, and so it's stopped there. And now we generate the supports, and we see now here our surface and line supports are generated. Take a look to them. We see that here in horizontal direction the fixed values are applied, and in Z and shear direction they are generated. Same applies for the line supports here, but they are only generated in that direction. Now we can start over to the loading. We don't need any more self-weight of the soil, because this is already applied within the constraint modulus method. So we delete this case. Now going over to the design situations, and we'll use the combination wizard for the ULS and the SRS quasi-permanent case. So we use the second load combination with one load step, and also want to import the elastic support coefficients with a great feature to fast up calculation time, and as well get other support coefficients from a load case, maybe SRS load combination to ULS. So we're searching for the corresponding from quasi-permanent for all of them. Go to OK. Go here also to OK. And now see there are some load combinations automatically generated. Now we see here the elastic support coefficients are will be calculated, and here they will be imported. To see the corresponding combination, at this point we will use automatically assign corresponding load combinations. And now we see they are visible here. We can also assign them by hand by taking a new characteristic SLS combination, setting the load the factor 1, and assign them by ourselves here. Now we can calculate all of them. As you will see, the settlement will be a little less than in the 3D calculation. What comes from the different behaviors of the methods, as well as of the implemented material behavior. Afterwards, we will check the settlements and as well the import elastic support coefficients, and we'll see the different behavior of the soil building interaction. So as you can see, it's much faster than 3D calculation, but it also needs a few seconds. And I forgot to show you something. It's within the static analyzer settings. You have an additional thing for geotechnical analysis for the 2D constraint modulus method. If sometimes the iteration can't find an equilibrium, you can give a higher number of iterations or a lower precision by a higher value here. But now we will see global deformations and can deselect all solids because they don't interest at this moment, but would show all surfaces. Now we see the overall behavior is like it was for 3D. We see a higher settlement on this column, and as well in the middle on this middle wall than a normal plate. At this point, we only want to see the base and also want to see the lines on the bases and not only the surfaces. So now we can also go through a result section and define this from here to net for the surface, and let's show the values on this result section. Now we see global deformation. It's mostly Z direction. That's true and right. And the characteristic, we have 1.7 compared to US definition from 2.3, 1.6. So, we can now check the elastic support coefficients on surfaces. At this point I would show it this one. Yes, that's the values I would show. And also within the support reaction, the elastic support coefficients for the lines. And we see in this and the other assigned, they are equal, so the input works as expected. So we're going forward to the next point, and I'll show you our next exciting feature, the anchors. Anchors are now available as a new member type within the Geotechnical Analysis add-on. They can be selected by the Added Member menu and automatically generate 2 new sub-members. This is first a tendon part without bond to the soil around and can only bear tensile forces, and a grout body with bond to the soil around, which corresponds to the member type pile with a pile resistance. And now go over to prepared model. You see here a slope stabilization for heavy goods traffic on top, modeled as 1 meter slice volume with supports only orthogonal to the side faces and constraint support on bottom. We have to select in the base data the Geotechnical Analysis add-on, and additional for a good representation of the stress state for the soil, the construction stage analysis, and for a later investigation about variable load, the structural stability add-on. I also prepared the materials, which is first steel S355 for the tendon part of the anchor, and a plate which will be based on top of the slope, on the side of the slope, sorry, and as well a concrete C3037 for the grout body, and the surrounding soil is modeled as a sand with a modified Mocoulomb material model with a cohesion of 10 kilonewton per square meter. Sections are also prepared. It's a round steel bar for the tandem part and a circular cross-section with 125 millimeters in diameter for the ground body. The steel plate will be modeled as a 20 millimeter surface. So now, starting with the anchors, I want to insert global parameters for the base resistances. You can download them easily from this knowledge base article, and we want to model it for empirical resistances according to Geotechniczna. And you find them, sorry for it, down here in the English version. I already downloaded them, and so I only import them. What we now have to do is to change some parameters. It's the material number of the soil, and this model is 3, and the cross-section number of the pile is 2. We will leave the bond length of the pile with 2 meter 50, but want to change the mesh fineness from the to double for speed up the calculation, but you can also try the original values. Furthermore, the resistance of the pile should be 0 for anchors. And now we're done, and the other values we need for the pile resistance will be calculated automatically by these formulas. So we start on with a new coordinate system and call it anchor, and select it by 3 points, the origin, right direction, and this upper top of the slope. Set it active, and now continue origin, and we want the first anchor to be in the middle of the slope. So we change the position by take a look in new 0.5 meters, and we to the middle of the plate and minus 10 millimeters. So we can model a surface contact. So change to the right coordinates and get the new member type anchor. Here you can select the start of the member type. It's the first or the last point. In our model, it's the first point. The unbonded tendon will be steel bar. We can select the length of the grout body from our global parameters, 2 meter 50, and select the cross section for the grout body. Also, we do a new high resistance and also use our global parameters. It's tau for shear strength of the skin. When we show the formulas, we can easily copy and paste here. And the shear stiffness will be Ks. Search for Ks, insert them, can also copy and paste. And for conclusion, also it's 0. We insert also sigma b and kb here. So we check the values again and see that's our calculated values. to OK and make a 6 meter long anchor. Now we see anchor is generated, and we see also the sub members are generated here. You can see them at the moment in standard, but can easily make them visible by selecting the objects generated by anchor. So here is the pile part and the tendon part. So we go further and do a new surface via the center for the plate. Should be 50 millimeters larger than the wrong thing. Now it's that anchor, and we want to do a second one, so selecting these nodes, and again the distance between the anchors will be 2 meters in -v. Get a 3 meter plate, and also copy. Oh, that's interesting. Now we can also copy them by selecting the anchor and the navigator. Also 2 meters. Copy. Now our anchors finished. And go back. Let's see here are 2 anchor types. And now we make the mesh refinement. At first, for the volume, also selected from global parameters, it's LFEVG. Okay, insert. Oh, I also want to show you something else that's very important. You see here the integrated objects for the solids, for the independent mesh. These are the lines for the pile types. And so they get also a mesh refinement according to their thickness, and it's easy by using only them. Select the lines, edit them, and get them a mesh refinement. New one, target FE length, global parameters, selecting this parameter, and now there is the mesh refinement. So next we want to go over to loads. See here our load cases: self-weight for the soil, the pretension for the anchors, and the vehicle load. We have to insert a pretension. Now, therefore, we can select tension parts, get a new member load on it with initial pre-stress of 100 kilonewtons. And now all loads are done. I'm going over and take a look to the console. Oh, something else is missing. We need our surface contact. So we select the plate and slope part of the soil. Get a failure under tension. Now it's generated, and going over to construction stages, which are also prepared. We have construction stage for the linearized stress, nonlinear calculation. Afterwards, the anchors will get self-weight, so the members, surface, and surface contacts will be active, and also pretension and the vehicle load. So we're going over and see our design situations. We only use the quasi-permanent part. We want to do the combinations by the combination wizard and consider the initial states from the construction stages. Construction stages have to look at the first undefined structure calculation for the state of stress, linearized by deactivating the material nonlinearity, activated the nonlinearity. Afterwards, they come the anchors with their self-weight, free tension, and the vehicle load. So you see here are generated load combinations with the structure modifications and the structure analyzing settings. And here you see the initial state and construction stages. And as said before, we want to do a critical load analysis by structure stability add-on with the nonlinear incremental method until 100 millimeters deformation. Additionally, I did result combination to see the additional contact stresses coming from the normal vehicle load to see if our model is big enough. So we now can do the static analysis for all of them, but I prepared already calculated model, and here you see the global deformations by load combination with the vehicle load. You see it's only the high deformation on the top, and if we go to the nonlinear stability analysis, we see that we're going further and not in the middle anymore, as preparing for a slope destabilization. And activating the anchors until a failure comes with little higher load. So we also get the section values. I would show you them as well. So you can check in the middle of our volume, and we want to see the internal forces, the normal forces in the anchors. You see here the pile part, it's raising up and going to constant volume value for the tandem part. And furthermore, we want to check the solid stresses, basic compression stress. See here, and the anchors have a high influence, as we see. Better we see it also on shear stress, maximum shear stress. You see it. Yeah, wonderful. So now see we now want to check the result combination to see our stresses in high values, and to a new window to check also the stresses in only self-weight load. So we see the contact stresses, surfaces on the slice, to a new window. The windows titled horizontal. Vertically, I want to show them. Don't want to see this, but there's two of them here. And here we see the stresses, the additional stresses from vehicle load, and here we want to check the self-weight of the soil. And see, there we can show each result, but we can, as you see, it's much less than 10% on the bottom. We only have a higher point on the upper right. Additionally, I want to show you calculation diagrams of the pile parts, as we see here. On the lower pile part anchor, the normal force is rising with the load and also the deformation in local X. Same applies for the upper anchor, and we now see here a combination of both of them. So go back to our presentation and want to show you our now new coming exciting features for the geotechnical analysis add-on, which will be a subgrade reaction modulus method, additional to the 3D and the shown constraint modulus method, a stability analysis via reduction of the strength parameters for soil, a new chem clay material model, and the model type 2D plane strain, which will be very beneficial for modeling such slices not by volume, but by a 2D slice. So thank you very much for your attention and give back to Andreas.
Thank you, Mark, for your presentation. I have an additional hint for you. You can get the steel joints add-on at a reduced price. You can get 21% off. And the offer is valid until the end of the month, June. For more information, just click on the button at the bottom, or you can scan the QR code on the right side here. Okay, that is also all from my side. I thank you for your attention. Thanks again to Mark for the presentation. Thanks to Juliane for answering the questions during the webinar. I wish all a nice rest of the day. Bye-bye.